Now we're going to go ahead and take a deeper look into limits. And if you remember back to last lesson, we talked about proving the existence of a limit depends on both the left-hand limits and the right-hand limits being equal to one another. So here's that definition. Okay, so let's take a look at the limit as x goes to 0 of f of x. We have two functions here, f and g. So we're just looking at the one on the left. As x goes to 0, from the left side, the y values approach -1, and from the right side, the y values approach -1. So this limit exists and is equal to -1. Take a look at the limit as x goes to 0 of g of x. From the left-hand side, from the negative direction, the y values approach -2. From the right-hand side, the y values approach +2. Those are different, so that limit does not exist. Right, we can take a look at a composite function. Limit as x goes to -2 of f of g of x. So with a composite function, we start from the inside, which is g of x. As x approaches -2, the y values are approaching 0. So if we look at our one-sided limits, as x goes to -2 from the negative direction, we'll go over to g. We're approaching a y value of 0, but notice we're approaching 0 from below. So we're approaching 0 from the negative direction. So we write the limit as u goes to 0 from the negative direction of f of u. Now we go over to the function f. As we approach 0 from the negative direction, we approach -1. As x goes to -2 from the right-hand side, from the positive direction, starting with the inside, we go to the function g. And as we approach -2 from the positive direction, the y values approach 0 from up above, which is the positive direction. And if we go over to f, the limit as our values go to 0 from the positive direction is -1. Those are the same, so that limit exists. It is -1. Okay, now if we look at the limit as x goes to 0 of g of f of x. So we're going to start with the inside, f of x. As x goes to 0 from the left-hand side, the y values approach -1 from below, so they approach -1 from the negative direction. So we take the limit as u goes to -1 from the negative direction of g of u. And as our x values approach -1 from the left-hand side, the function g approaches 2. The limit as x goes to 0 from the right-hand side of g of f of x. So we start with f. As we approach 0 from the right-hand side, the y values approach -1 from below. So we're approaching -1 again from the negative direction. Go over to g. As we approach -1 from the negative direction, our y values are approaching 2. So this might be kind of surprising, because if we just looked at f of x when x is approaching 0, the values are approaching -1. And if we go over to g of x, we can see that it's discontinuous at -1, which might lead us to believe that this function, or that this limit, does not exist. But the limit does exist, as we can see when we examine both of the one-sided limits. Because in both cases, f of x is approaching -1 from the negative direction. So when we get to g of x, we're approaching -1 only from the negative side. So that limit exists. And now we're going to take a look at the sandwich or the squeeze theorem, which gives us a method of evaluating some limits. So here it is formalized. We have three functions, g, f, and h. So f is greater than g and less than h. It's always in between those two. And if the limit of g equals the limit of h, so the smallest function and the largest function, they both approach the same value L, since f is in between, the limit of f must also be L. And here we have the squeeze theorem in English. So f is always between two other functions, g and h. If g and h approach some value, then f also approaches that same value. So we'll use the squeeze theorem here to prove that the limit as x goes to 0 of x squared sine of 1 over x equals 0. We know that sine of anything is 1. The largest it can be is 1. So x squared sine of 1 over x has to be less than or equal to x squared. And we know that the smallest value of sine is -1, so x squared sine of 1 over x must be greater than or equal to -x squared. So we now have that x squared sine of 1 over x is greater than or equal to negative x squared and less than or equal to positive x squared. We know that it's always going to be between those. If we take the limit of each of these functions, we can just use substitution for negative x squared and positive x squared. As x goes to 0, those both go to 0. Since the limit as x goes to 0 of x squared sine of 1 over x is greater than or equal to 0 and less than or equal to 0, it must be equal to 0. You can explore this on your calculator. I'll show the graph here on the next screen. Here is the graph of y equals x squared. Here's the graph of y equals negative x squared. And here is the graph of x squared times sine of 1 over x, which we should expect to always be between these two functions. And as x gets close to 0, we would expect it to also have a y value getting close to 0. Let's see what that looks like. There we go. It bounces back and forth between those two, and it squeezes right between them. And we can see from that 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 limit actually is approaching 0.